Now we have the last one, which is the static or the leakage current. Where is the leakage power? The leakage power occurs here at the um, at the transistor. This is the cross section of the transistor. This is the channel. The channel is supposed to be on when the VDD is when the voltage, the VG is greater than the threshold voltage, right? But when VG is less than the threshold voltage, it is supposed to be off. However, this sub-threshold current is present when VG is less than threshold voltage. That means when the gate is supposed to be off, it is supposed to not create a channel and not have current, but there exists this current. This is known as the sub-threshold leakage current. Okay. The other leakage current is the current because of tunneling from the gate to the channel, and this is known as the gate oxide leakage current. So the leakage power is just very easy. It is just I times VDD, and I leakage is the two current, sub-threshold current and I gate. Okay, so the leakage power here, you can see over here, sub-threshold leakage occurs when the circuit, this is the transistor, the model is like a switch. When the switch is supposed to be off, there is supposed to be I0. But instead, I is not zero, and this is known as sub-threshold leakage. The other one is when the current here at the gate is supposed to be zero. There should be no gate current, but the gate current is not zero, and this is the gate leakage current. Okay, so for the leakage power, the sub-threshold current is the dominant factor. This sub-threshold current and gate leakage current occurs very much nowadays because the transistor technology is becoming very, very small. And because of this, your channel here is very, very small, right? This is like, for example, 6 nanometers. So it is very easy for the current to pass through, right? When it's supposed to be off, that it is very easy for the electrons to pass through because it's very close by. So it is now among the dominant current. Okay? So that is the sub-threshold current, and this is the gate leakage current. There may also be a drain junction leakage current, and this occurs at the output. So the leakage power is VDD multiplied by the sum of all these leakage current. So leakage power is a lot dependent on the threshold voltage, right? As you scale the supply voltage, what does it mean by scaling the supply voltage? It means when you are reducing the supply voltage, right? And when you reduce the supply voltage, let's say from 3 volts to 1 volt, you must also reduce the threshold voltage. When you reduce the threshold voltage, you make the transistor smaller. It will make it easy for the sub-threshold current to occur. And this will be a dominant component in the power dissipation. Okay, as you can see here, when V threshold is 0.4, the sub-threshold current is this value, around 10 to the minus 11 or like this. And as you increase the gate source voltage, the current will increase. But when you reduce the V threshold down to 0.1 volt, you can see that the sub-threshold current increases. Okay, so this will make leakage power be higher. Okay, so let's look at the process parameters. TSMC is the Taiwan Semiconductor Foundry. This Taiwan Semiconductor Foundry is very, very famous now. It is a manufacturer of all the major chips. Intel used to be its competitor, but now Intel also sometimes asks Taiwan TSMC to fabricate their processors, right? So when you look at the process, they will name the process like this: CL018G, It depends. So each process or each technology, they will have a different name. And usually this 1/8 will be respective, will reflect something. So in this case, this one, this is the process name. It is, or maybe like something related with the voltage. So you can see, let's look at this one, CL018G. The VDD is 1.8. The T oxide, or the thickness of the oxide, is 42 angstrom. Angstrom is 10 to the minus 10 meter. The gate length is 0.16 micron. The saturation current is 600 over 260 microampere per micron, micrometer. Leakage current is 20. Threshold voltage is 0.4. This is the frequency, 30 gigahertz. Okay, so now we move down the technology, right? So as we move, you shrink as we move down the technology, as you can see over here. This one, let's look at the middle one. This is a smaller gate, 0.13 micrometer gate, smaller technology, voltage about the same, 2 volts, thickness of oxide about the same, leakage current is much higher. Leakage current is much higher when it has reduced a bit the threshold voltage. Frequency is higher, 43 gigahertz. Okay, now let's look at the last one over here. This one, they reduce the VDD much more. VDD, this is a smaller technology, 1.2 volts. Thickness of oxide is 24 angstrom, also reduced from 42. The gate is much smaller, half the size of the initial one, 0.08 micron. Leakage current, look at this, 13,000 picoampere per micrometer. Very high current, very high leakage. Threshold voltage is much, much lower. So you can see here, when you reduce the threshold voltage, the leakage becomes much higher. Frequency is also very high. This small gate can have very high frequencies. Okay, any question? All right.
Madam,
Ah,
what is the effect when the leakage current is so high, like 30,000 compared to the 20? Is it going to increase the power consumption, or is there any glitch dalam chip tu?
there will be, it will increase the power.
Power
This
only
is
lah.
the power.
Okay.
Ah, there might be also glitch because now the subthreshold current, the transistor is more often on when not supposed to be on, right? Because the leakage is due to this. So you will have less reliability of your chip. So, so VLSI engineers there are many types of VLSI engineers. There are those who are reliability engineer. They look at the process. They look at this process. They say leakage current. You have to then check the reliability of the circuit. The transistor. Is the transistor reliable? Is it 99% reliable, 98% reliable? What can you do to improve the reliability? Should you increase the thickness of the oxide? Then they will think on what to do to the process. Okay,
Okay, madam.
good question. All right, so now leakage versus temperature. Of course, if you heat up your chip, there will be higher leakage. You can think about it like this. When you heat up your chip, the electrons will have higher energy, then they can easily go through from the drain to the source, right? This guys, the current is supposed to be from the right to the left. Now the electrons over here have high energy, they become easier to, they have more energy to pass through the channel when there is, even if there is no channel. Okay, so leakage current components, we've gone through this. Subthreshold conduction, subthreshold, reverse bias, PN junction, ID. This is reverse bias, PN junction conduction. In your transistor cross section, let's say this is N, it is in a P well, there will be a diode here, right? This is a PN junction, so there will be a diode here. I cannot draw very well with my mouse. Okay, anyway, you imagine this is a diode. All right, so this is the diode. So, but because you are putting the voltage here and there's no voltage here, so this PN, this PN junction is reverse bias. But even though it's reverse bias, you can have reverse bias current, which is supposed to be very, very small. Okay, so this is the leakage part, the reverse bias PN junction conduction. It is small, but when you accumulate all of them, there will be a lot. Okay, there is also another thing called gate-induced drain leakage, GIDL, due to the tunneling at the gate drain overlap. Okay, so now where is the gate drain overlap? You can look here again. This is the gate, right? And if you have a self-aligned gate, this should be perfectly matched here. This is your gate, and this is your source, and this is your drain. So if it should be perfectly matched. But sometimes the process is not perfect, and especially if it's in nanometer scale, the drain, when you bombard the ions, it might go a bit more like this. Change color. It might go a bit like this. This is your drain, and even your source might be like this. Because you're doing ion implantation, sometimes when you implant the ion would like to move a little bit here. The process is not perfect. So there is an overlap between the gate and drain, this area. This area, because of this, there might be some current here. And this current is known as gate-induced drain leakage current due to the tunneling. There can be tunneling from the gate to the drain at this overlap. Okay, and this is IGDL. And then this one, that one was at the drain. Now this is at the drain source, punch through, IPT due to the short channel and high drain source voltage. As we have drain source punch through due to the short channel and high drain source voltage. Okay, so as you have a smaller and smaller technology, right, your drain source will be closer and closer together. This channel will be small, so there might be, it is like the sub-threshold current. It can still go through, and this is even maximized when the channel is even smaller. Okay, so this is known as the drain source punch through current, and also the high drain source voltage. So when you apply a voltage at this part, the drain and the source, you remember there is one voltage over here. This is known as VGS here, and there is one voltage known as VDS over here. This is between the drain and the source. Okay, so VDS, when your channel length is small, the voltage over here will be very, the voltage over here, let's say, is 1 volt, but it's 1 volt across 1 nanometer or 6 nanometers. So the voltage density is very high in this area. Because of this, because of the presence of this voltage, this is what will give the energy for the electrons to move through, even though there is no real channel, right? You apply a drain source voltage, it is not yet higher than the threshold, but it has still, the electrons has enough energy to move from the drain to the source. Okay, and the final one is the gate tunneling, that is the gate through the tin oxide.